वो ट्यूटोरियल में दे देता हूँ अपना ट्यूटोरियल। So here you have the next tutorial, and I think we have already decided the date of tutorial 3. That was Monday. What is the date on Monday? 21st, 20th. So 20th, 12 midnight. Yes? Any suggestion for the date? Okay. Okay. So, do you know the relationship? We will discuss that. I have not yet discussed it, so don't worry. We will talk about this tutorial. Can you tell me, we have discussed this, can you tell me the relationship between PGA, PGB and PGD and the response spectrum? So, you are familiar with the shape of the response spectrum? Okay, this is the typical shape of the response spectrum. So, what relationship it has with PGA, PGB and PGD? How amplitude, different amplitude parameters are related to the shape?
Yes, V equal to omega into SD. Yes, velocity equal to SV equal to omega.
Okay, so one relationship is that you can get SV. That is
Omega into SD.
SA by omega. So that is SA into T over 2 pi. That is one relation. And then you can get SG as SA over omega square. So that is okay, fine. But how do you get PGA, PGB and PGD from there?
Sir,
What relationship this has with PGA, PGB and PGD? Have you heard about tripartite plot of response spectrum? Have you done that? What is tripartite plot?
in one graph there are three relations shown: velocity, displacement, and acceleration.
So, using these relationships, you have plotted earlier in the first semester SV versus T, and how it was looking like. Wherever this is linear, it was parabolic. Wherever this is constant, it was linear. When it is proportional to 1/t, it was constant, and then it was reducing. So this is the typical shape of SV, velocity spectrum. Okay, and similarly, we have plotted SG versus T. So this becomes cubic parabolic, then linear, and then it becomes constant. So this is the typical shape of displacement responses. Okay, so if you know one, you can plot the other two. Any one, if you know, from that you can obtain the other two. Only thing is there is a transformation using these two relationships between SA, SV and ST. Okay. And why, how these relationships are possible? These are possible because we have defined pseudo acceleration and pseudo velocity. So we have used pseudo acceleration, not the real acceleration. We have used pseudo acceleration, and we have used pseudo velocity, not the real velocity. is it justified to use pseudo acceleration and pseudo velocity? Why not to use the real acceleration and real velocity? What was the reason to use pseudo acceleration in place of real acceleration?
They are almost equal.
Okay, so if equal, then why not to use the real one? Why to use pseudo?
If we have integration from acceleration to velocity, exactly different. As integration from displacement to velocity to acceleration, we have some constant integration. Then we have to just neglect some terms, compromise some terms. That's why it is pseudo.
No, we are not. See, in the starting of the time history, the acceleration, velocity, and displacement are 0. So you know the initial conditions. When you know the initial condition, you can calculate the constant of acceleration, constant of integration. So there is no problem of calculating real acceleration and real velocity. You can calculate real acceleration and real velocity. So how you will get real acceleration and real velocity?
So we ignore the damping.
We ignore the.
Damping. That's why it is pseudo.
But why to ignore damping when you can consider damping? Okay, why you are ignoring damping? What is the need to ignore damping? You can consider damping, and you have seen that spectral acceleration. We are not ignoring damping. We have seen response spectrum also. We are plotting for different dampings, so we are not ignoring damping there. Okay, but ignoring damping cannot be any logic to use pseudo. What is the fun in using pseudo? Why we want to use pseudo? I explained this in last semester also.
So it is the acceleration recorded on the structure itself.
Yeah.
So if you want to have the response of a single degree freedom system, then directly we can measure it on the structure. So that's why we don't use the ground acceleration.
I'm not saying structural acceleration or ground acceleration. I'm talking about the real acceleration of the structure. Okay. So suppose this is my structure, a single degree freedom system, a simple building, resting on 4 columns. I have applied a ground motion here, and I will get a response here. So suppose here I have applied UG double dot, here I will get U double dot. Both are function of time. I can take peak of this, this is called PGA, and here I can get U double dot max. I can get. This is possible using experiment. I can put my single degree freedom system on shake table and test it, or I can do it numerically as well. You know numerical methods also by which you can calculate U dot, U double dot. Okay, so U double dot you can obtain. So there is no difficulty in obtaining U double dot max. You can obtain, but we don't do that. Rather than we use in place of this omega square U max. Not U double dot max. We use omega square U max, and this omega square U max, what is U max? U max is nothing but SD or D, capital D, the symbol we use. So we obtain essay like this, and this we use to plot our response spectrum, not this. Why?
The answer is in this expression because this omega is the frequency of this.
The structure?
Yes.
Yeah.
So this will let us know that what kind of acceleration will be induced in this structure.
And we know from here itself. Here also we are knowing the acceleration only, nothing else. So the answer lies, what will you do with this acceleration? What is the purpose? Why we are doing all this? What is the purpose? To get the force. Forces for design. Let us say designing the column or wall which is here. So if you have to know what forces are developing in this, the force here is this mass, whatever is this mass into U double dot, that is inertia force. Are you interested in this? You are interested in these moments and this shear is V. What is this V equal to? V is equal to K into U. V is actually also a function of time, U is also a function of time. And it is not equal to mu double dot. So it is not the mu double dot in which we are interested. That is inertia force. We are not interested in inertia force. We are interested in the force which is occurring in the members, in the columns, and that is equal to K into UC, not M into U double. That you have to keep. And I am interested in maximum value of this. For design, I need the maximum value. So maximum value will be K, because K is, if I am considering a linear structure, then K is constant. T max. And what is this? This is K into SD. And what is K? K is M into omega square. That is M into SK. So it is the pseudo acceleration which multiplied with mass will give us column forces, not the actual acceleration. Okay? So it is not ground acceleration times the mass which is giving us the member forces. It is not structural acceleration times the mass which is giving us the forces. It is pseudo acceleration times the mass which is giving us column forces. And that is because the column forces are given by this expression, not by this expression. Okay? A.K. Chopra in his book has nicely explained this. I have explained it in the last semester. You have forgotten it. Okay, but I want you to never forget it. That why pseudo acceleration? Why not real acceleration? Different answers come. Some people tell pseudo acceleration we use because it is difficult to obtain real acceleration. It's not. Okay. In case of an undamped system, if the damping is 0, then you can see that both are equal. For undamped system, pseudo acceleration is, you can see from the equilibrium equation. Okay, so whatever is this mu double dot, the same force has to be transferred, there is no other force. But when damping comes into picture, there is additional force due to damping is also coming. So in case of undamped system, this one. But as the damping comes into picture, these differ. And the difference for low damping is small. What is low damping? Of the order of 5%, 10%. In that range, this difference is negligible. Chopra has plotted the curve of difference between these two quantities with damping, and there you can see for a smaller damping the difference is very little. So this is also treated as the acceleration of the structure. Okay, but as the damping increases, the difference emerges, and it is not. So it is not theoretically equal to this. We are not using because it is close to the actual acceleration. We are using it because we are interested only in it. We are interested in member forces, and member forces are given by pseudo acceleration, not the actual acceleration. Yes. Why the difference arises? Because you can see if there is a damper also here. Okay, so there will be a force C dot and its component in this direction. So you can see that now that if you are taking equilibrium, what you are doing, you are taking equilibrium in equation of motion. So this plus this, okay, that will be equal to 0. Okay, so because of this force, now these two are not equal. If this force is not there, then these two are equal. Okay, because this force is also there, these will not be equal, and you will not get pseudo acceleration same as the real, because of the presence of damping. If the damping is small, both are close, nearby. If the damping is large, 20%, 30%, then both are not same. And in fact, the real acceleration we don't need. Until unless, when we will need real acceleration? When I have to design anchorage of my equipment on floor, then I will need the real acceleration. Then pseudo acceleration is not going to happen. There I will need, suppose I want to determine whether this will be stable in case of earthquake or not, then I need what actual acceleration is occurring at that floor level. And that acceleration will decide whether it is going to topple or not. And if I have let us say an equipment here, a tank, which I want to mount on the floor, then the forces which will be occurring on that will depend upon the real acceleration of the structure. Those will not depend upon spectral acceleration, pseudo acceleration. Okay, so there I will need the real acceleration, but for the design of the structure, I need the member forces. Member forces will depend on displacement, not on acceleration. And displacement I have multiplied by k, and k I have substituted as omega square into st. M omega square, sorry. So when I replace k by m omega square, then I get. And this relationship, k is equal to m omega square, this is also valid in case of undamped system. As the damping comes, k, the relationship between k and m omega square will change. Okay, the damping will affect the frequency. Okay, so there this relationship is also not valid. So all these substitutions are valid only for undamped.
Sure.
Yes.
Whenever I want to get the response spectrum of any building of means
Response spectrum is not of building.
Not of
response spectrum is of earthquake motion.
earthquake motion of different time periods,
Right.
natural time periods.
Right.
Then first, let us say this is one building, this is another building, and at T1 time period, this is a T2, T3, T4 like that. First, I will what to do, I will write equation of motion, mu plus u plus u of this. This u dot double g is the data coming from the data motion. That data I am getting, now this u dot double g I am using here. This should be the ground or above that one?
Ground.
Ground, okay. This one
Wherever G is appearing, it is.
it is that one. Okay. Then I will get eigenvalue problem. Here.
No. Response spectrum, no eigenvalue is there. Response spectrum is, just understand, response spectrum is all single degree freedom systems. These are all single degree freedom systems, and these are subjected to some earthquake properties.
Yes. I want to reach from that ground motion to response spectrum.
Right. So what I will do with this, I will calculate the response of this.
Yes.
Response of this. And I will take the peak response wherever it is occurring. Say it is occurring here, it is occurring here, it is occurring here.
Yes.
So I will get the peak response. That peak response will give me SD. Let us say this is period T1,
Yes.
this is T2, this is T3. So this will give me SD at period T1. This will give me SD at period T2. This will give me SD at period T3.
Yes.
Okay. From here, I will multiply this by T square by 4 pi square. So as at T1, I will get SD at T1 into T1 square divided by 4 pi square. No, ulta. It is S into omega 2 pi by T. So like that I will get SD, SAT, and so on. And when I will plot this, SA with different values of T, let's say T1, T2, T3, and so on, corresponding values, I will get a plot. This is our response.
Yes. The acceleration here, here we are using at the base of the building.
Acceleration acceleration which we are getting from the earthquake is at ground.
Yes.
So we are using at ground only. So input is at ground level. Output is at the top of the structure.
And from ground to top, how you are converting that acceleration? By using omega square relationship, S equal to, now you have.
No. From ground, UG double dot, I am analyzing my structure. This is UG double dot T. I will analyze my structure. Single degree freedom system. Analysis of single degree freedom system for a ground motion, you know.
Yes.
Okay, so I will analyze that, and from that analysis I will get U T, and maximum of that UT is my SD.
Yes. But this UB max is corresponding to the when acceleration is applied at the base of the
Right.
building. Now I
Ground level.
ground.
It is at the ground.
It is at the ground. Now I have to convert the acceleration at the top of the building for delta O.
Yes.
Now how will I convert those coordinate into delta?
By analyzing single degree freedom system, you know how to analyze single degree freedom system?
Yes.
For earthquake,
Yes.
you have to use some time marching scheme.
Yes.
So you will perform time history analysis. So for this time history, you will perform analysis of this, you will get this response.
That I am getting, but I want to convert base acceleration, ground acceleration to the delta
Top acceleration.
Top acceleration. So
Yeah.
how will I
So
convert
ground
that?
acceleration to top acceleration, you can't convert directly. For that, you have to do analysis. You have to do time marching, time step integration. There is no multiplication by which you can convert this to this. Okay? So you have to determine response of the single degree freedom system. That will depend upon the period and damping of this. What you have studied in your theory of vibration. So this transformation is not like this, that you will multiply by this something, you will get this. You can't do that. You have to perform analysis of the single degree freedom.
Yes, that's what I am saying. That here time marching I will do.
This is not single degree freedom system problem.
This is multi-degree.
Multi-degree.
So for that I have to do analysis for means I want to get maximum response of this, maximum response of this, maximum response of this. For that I will take equation of motion. This U.G I calculate from earthquake data motion model, and that I will
I have obtained from the record.
records. Then from that I will get for different frequency omega 1, omega 2. For this is say 3 degree system.
You can't get response spectrum for 3 degree freedom system. That's what I am trying to say. Response spectrum is defined for single degree freedom systems of different frequency, not a multi-degree freedom system which is having 3 frequencies. For that there is no response spectrum. Okay? So response spectrum is representing the response of a number of single degree freedom systems with different frequencies. It is not for multi-degree freedom system. Okay? So is your question still remaining or? Okay. So you were perhaps relating it with the multi-degree freedom system. That's why you are getting it. So response spectrum system is not for multi-degree. Okay. It is for single degree freedom system. If I want to analyze my multi-degree freedom system for response spectrum, what I do? I convert my multi-degree freedom system into a number of single degree freedom systems. And then I analyze. Because response spectrum can give me response of only single degree. It can't give me response of a multi-degree freedom system. To get the response of multi-degree freedom system, first I have to convert my multi-degree freedom system into a number of single degree freedom systems, equivalent single degree freedom systems. Then I will get response of those single degree freedom systems from response spectrum, and then I have to combine those to get the response of multi-degree. Okay. So response spectrum is the most fundamental concept which we use in earthquake engineering. All of you should be clear how it is obtained, how it is expressed, how it is related with other ground motion parameters. Okay? So any question? So we can convert the pseudo acceleration spectrum into pseudo velocity spectrum and displacement spectrum. Keep in mind, displacement is not pseudo. Displacement is real. Only velocity and acceleration are pseudo.
So why that displacement is real and not velocity?
Because the force will depend upon how we have calculated it. How did I obtain displacement? I am interested in forces. Forces have to be real. Forces are stiffness times real displacement. That is same as mass times omega square. Okay, mass times omega square equals d. Everything is real till this point. This I am replacing by SA. I am calling it an acceleration. But omega square equals d, is it an acceleration? It is not. It is not acceleration. But its effect is very similar to acceleration, because mass into acceleration gives me the force. Its units are also like that of acceleration. What is the unit of SD? Meter. What are the units of omega square? Radian per second. Radian per second. Radian is unitless, so it is per second. So units are meter per second square. Okay. If you multiply it by mass, you get force, some force. That force is not inertia force. That force is member force. Okay. So its behavior is similar to acceleration. Its units are similar to acceleration, but it is not acceleration. So what should I call it? There is a quantity which behaves like acceleration. Its units are also like acceleration, but it is not acceleration. So what should I call it? Pseudo acceleration. That's why I call it pseudo acceleration. But only acceleration, this omega square SD, this is pseudo. SD is not pseudo. SD is real. Okay. So when we are plotting the response spectra like this, SD is real, omega times SD, that is velocity, that is pseudo velocity and pseudo acceleration. Okay. And why pseudo acceleration? Why not real acceleration? Because it is the pseudo which is serving our purpose. Real is not serving our purpose. So we are not interested in real acceleration. We are interested in pseudo acceleration. Because when I multiply that by mass, I get the member forces directly, and I am interested in member forces, not the inertial forces. So member forces I will use for design. So that's why I am interested in members. Is this clear? Yes. Related. Because keep always in mind, we have to estimate forces. So the forces here in this column will depend on relative, not on the absolute displacement. The whole building moves, doesn't cause any force. Okay. So only the relative displacement with respect to the ground, which I am getting, which we are representing by U in terms of the terminology used by A.K. Chopra in his book. It is U, not UT. Okay. So UT is the absolute, total. It is U, which is the relative displacement, the displacement of the mass in the single degree freedom system with respect to the ground displacement. That is required. And that relative displacement, peak value of that relative displacement, when we multiply by omega, we get pseudo velocity. When we multiply by omega square, we get pseudo acceleration.
Sir, for
Yes.
obtaining response spectra, I need to take some record data.
First of all, a very common mistake you will do, spectra is plural, spectrum is singular. So when you are talking about one spectrum, it is a spectrum. When you are talking about number of spectrum, then it is a spectrum. Okay, so it is because in Hindi, spectra appears to be singular. Okay, because ladka is singular, ladke is plural. Okay, so we have this tendency to call spectra as singular. So please keep in mind, be careful, because when in an interview you are saying I have used spectra, so this will give a wrong impression. Okay, so be careful when you are talking about single spectrum, call it spectrum. Okay, it's not ladka. Okay, keep that in mind.
Spectra is a set of spectrum.
Number of spectrum. Spectrums are spectrum. Okay, so English is slightly different than our language. Yeah. Now
I need to get earthquake motion data of records U.G.
Right.
Which U.G should I select? Which data should I
So
select?
any ground motion you can have, each ground motion will have its unique spectrum. So if you take a number of ground motions and plot their response spectra, you will get different shapes.
Yes, but what design which I have to consider? How?
Okay, so these will be obtained from different ground motions. Those different ground motions will arise because of different magnitudes and different distances at different sites you have recorded. Okay, none of those is similar to your site. So what should we do?
We will give maximum.
So what maximum we can't, because what if you are using maximum, suppose one is recorded in western coast of America or in the Himalaya, okay, and you want to use that in Hyderabad, is it okay? Is it justified? So maximum we can't take. So what we have to do, we divide it into two parts. One is the shape of the response spectrum and another is amplitude. Okay, so amplitude you can define in terms of PGA, PGV, PGD. Shape, this is representing frequency. So how to get shape? First you have to normalize it. Okay, because these different earthquakes, let me plot again. Some earthquake may be like this. Another earthquake may be like this. So if you see, these are having different values of EPGA. These EPGAs are different because an earthquake ground motion which is caused due to a larger magnitude earthquake at lesser distance, that will give me higher EPGA. Okay, and another earthquake which, or even the same earthquake, if I record at a distance away, then the EPGA is going to reduce. Okay, so the shape is also changing, EPGA is also changing. So what we do, we normalize these first with respect to this ordinate, EPGA. And you know, for others who have not attended the last semester, what is this EPGA? Effective peak ground acceleration. That is full form of this abbreviation. But what is this? EPGA. So EPGA is nothing but zero period acceleration. Zero period spectral acceleration. Spectral acceleration corresponding to zero period. But can you obtain the response, or you analyze a structure which is having zero period? Can you perform analysis? Zero period means what? Zero period means that the stiffness is infinite. Okay, so can you do that? It is not possible to solve it. Okay, so what we do, we take it corresponding to actually 33 Hertz frequency or 1/33, that is 0.003 second peak. Point 003 or 0.03? 0.03 second. So it is close to zero because you can't analyze the structure, you can't get response for at zero. Okay, so if you see it in close up, actually it has a flat portion. So in this range, this period, this corresponds to 0.03 second. Okay, so that value we call EPG, zero period acceleration. And what it is representing? Physically, physically which structure will have zero period or which structure will be very rigid. If I take a concrete block and embed it into soil, then this is something like zero period structure. And when it is subjected to ground motion due to any earthquake, UG double dot, what will be its acceleration? Same as that of the ground. Until unless this is very heavy. If it is very heavy, then what will happen? There will be interaction between the soil. It will try to move differently than the soil. But if it is lightweight, rigid, okay, small, then whatever we have here, same we are going to have UG double dot. So this UG double dot is equal to EPG or peak of this. So this UG double dot, this is taking a measure of PG, EPG. Okay, so EPGA is a measure of PG, and most of the times you will see when they are talking about PGA, actually they are talking about EPG. Okay, so this you obtain from response spectrum. PGA you obtain from the record of the ground motion. Okay, that record of the ground motion you apply on single degree freedom systems, number of single degree freedom systems, and you get the response spectrum. Value of that at zero period, you will get EPG. Okay, and what we do, we normalize these with respect to the EPG, and when we normalize this with respect to the EPGA, all the response spectra which we have considered, they will have the same initial position, but these may change. This point becomes same, and I have divided those by EPGA, so this will become 1, and this I can call as SA divided by EPGA. And I do it for a large number of earthquakes, I will get a shape like that. That's how we get the normalized response spectrum or spectral shape. So what is given in the codes is a spectral shape. This spectral shape needs to be multiplied by EPGA. That will be equal to SA. So what is given in our code, SA by G, and it is termed as a response spectrum. It is not response spectrum. It is a spectral shape. Only the shape of the response spectrum is given. That you have to multiply by EPGA. And what is EPGA in our code? EPGA is zero period acceleration so this EPGA is zero period acceleration ZPA, that is equal to Z, the zone factor. So what is given in the zone factor is the value of EPGA, which is close to the PGA, the maximum PGA or average PGA expected to occur in that region. So each zone is a region, and in every region there is a corresponding zone factor. What is that zone factor? That zone factor is EPG. Okay, and when we multiply that with the spectral shape given in the code, then we get the response. So what is given in the code? SA by G versus T, it is incorrect. Actually it is SA by Z. So 1.0, 2.5 and 1 by t. It is not SAIT. It's not correct to say it SAIT. The correct term is SAIT. That's why you have to multiply it by Z, Joule factor, or ZPA, zero acceleration, another name for the same, or EPGA, another name, or PGA, loosely we call it PGA also. Okay. But to be precise, it is EPGA, which depends on PGA, but it is not again equal to PGA. Yes.
Here SAYG, so this is moving angular ratio EB equal to A into W. So the EB should be M into A, acceleration. So there we use W, so to appropriate that W we use G in SAYG. So it should be SAYZ equal to G.
Okay. So what is Z? Z is actually representing pseudo acceleration. Okay. What will be the unit? And similarly SA, that is also representing pseudo acceleration. Units of pseudo acceleration and acceleration are same. Okay. Commonly used units, meter per second. Meter per second. Okay. And force V is obtained as M into SA. Okay. But meter per second square is not the only unit of acceleration which is used. There are other units also. Most commonly unit used for this in earthquake engineering is G. Acceleration is represented in terms of G also. What is G? 9.81 meter per second square. So G is also used as a unit, like the pressure when we are measuring. Sometimes we measure it in terms of bar or atmospheric pressure. Okay. So how many times of atmospheric pressure it is, or what fraction of acceleration due to gravity is this acceleration? That is another way of expressing. And in Japan, they use GAL. What is GAL? Anybody remember? Centimeter per second square. Okay. So they are using GAL because G is in fraction. Okay. When you convert this into centimeter, it becomes, suppose it is 0.36 G. In GAL, how much it will be? .36 G in GAL. Hmm? 0.36 G in meter per second square, how much it will be? In meter per second square, 0.36 in meter per second square, 3.6, and in centimeter per second square, 360. So you will get 100, 200, 300, 400 in that range. Okay, so that sounds, I mean, when you are expressing that, remembering that becomes easy. So in Japan they are continuing with that. So their design values are like 100 gal, 200 gal, 400 gal. That way they talk. We talk 0.36 G, 0.4 G, 0.2 G, 0.1 G in that. Okay. Meter per second square is not that common unit. So unit we are using is G. And when you are using the unit of G, what will be V? V will not be M into SA. V will be equal to W into SA. If SA is in the units of G. Okay. So in our core response spectrum, what we are writing is SA by G. Actually, and when you are representing SA in G, it is a fraction. Isn't it? What are the units? What does G means? It is just a fraction. 0.36. Okay. So you have to simply multiply it by a force unit to get force. So it, when multiplied by weight, which in itself is a force, when you multiply it by this fraction, it becomes a ratio. So this is actually SA in terms of G divided by Z in terms of G. So it becomes unitless. Okay, so that G which we are giving SA by G is not actually G, it is Z.
Sir, the purpose of dividing this response spectrum by EPGA is to get normalized or just another meaning.
Just another meaning? What another meaning?
Let's say earthquake was occurring in America, and there I have put some concrete block of infinite thickness. Same block I have kept in Turkey here. Now here soil conditions are different, here soil conditions are different. So response of same earthquake for that block and for this block same earthquake will be different.
So when you say same earthquake, what do you mean by same earthquake?
Same earthquake means
Same magnitude?
Same magnitude and same intensity.
Same intensity. So when you have said same intensity, okay, then it means that UG double dot plot is same. Okay. And if UG double dot plot is same, then if you put a concrete block here or in America, it will be same. The local side effect, if the soil is different, then UG double dot cannot be same.
It will be different.
It will be different. So here we are expressing it in terms of one ground motion. So one response spectrum is representing one ground motion. That means the unique ground motion at that site.
That's why this
And no two ground motions are same, I told you. So that's why which shape I should use. So I will consider a large number of earthquakes and I want to normalize those. Where is that should go? So number of earthquakes. Those earthquakes are occurring. If suppose I have to take average of these earthquakes, how will I take average? If these earthquakes are suppose these earthquakes are like this. If I take the average of these, that average will be erroneous. So what we do, first we normalize them. We bring the EPGA of all of those at the same level.
But sir, when you are dividing these coordinates by some EPGA, they are shifting just
Not
by
same EPGA.
same
Their own EPGA.
their own EPGA.
Yeah.
Each coordinate is shifted by some same amount.
Right.
So what is the difference in shape? Shape will be at that only.
Okay.
If you shift each coordinate by same amount below.
But the
shape,
average value will be different. Na? Shape will remain same.
shape will remain same.
But the value will be different.
Yes.
So I am interested in averaging the shape. If I do averaging of the shape or I do averaging of the value, suppose one earthquake is having a value of 8 times of the other earthquake and I take averaging, then what will happen? That 8 will govern everything.
Yes.
So I am not going to get same influence from all the ground motions. The stronger ground motion will have larger influence. So to reduce its influence or to make their influence same, I am dividing by the corresponding EPG.
So comparing those different earthquake motions, we are getting them at an equal level, so that we can compare it and add to both together.
Right. Okay. Okay. So we can plot 3 types of response spectrum: pseudo acceleration, pseudo velocity, and displacement. There is a representation of response spectrum in which we can plot all the 3 shapes in one graph. Okay, and what we do is, here we take either T or frequency, period or frequency, both are just opposite of each other. The period will increase left to right, frequency will increase right to left. Okay, then here we plot spectral velocity. Then we take, okay, let me do one thing. SA, okay, that is omega times SB or 2 pi by T times SB. Let me take log of this. Log SA. What will be that equal to? That will be equal to log 2 pi, okay, plus log SB minus log. Okay. You agree? Log 2 pi is a constant, and suppose I want to plot a constant SA line where SA is constant. So what will be that? This C1, that will be equal to C2, this is another constant, plus log SB minus log. Yeah, Kavan, your voice is disturbed. So I can take this as log, I can write log SB is equal to log T plus some constant C, which is C1 plus C. What is this equation representing? This is representing a straight line, and the slope is positive or negative?
Positive.
So if you draw, and how much is the slope? 45 degree. 1. Okay. So if you draw a line with positive 45 degree slope, what it is going to give you? It is going to give you a constant SA line. Okay. So if in place of SB I take log of SB and here I plot log of T, okay, and when I plot these lines, only the constant will change because C1 is going to change depending on what value of SA I have, the constant will change. These are representing different values of SA. So what does that mean? That I can plot SA on this axis, 45 degree opposite axis. So this, along this line, I can measure SA. You agree? If I take SA is equal to 0.1, let us say 0.1G, this line 0.2G, this line 0.3G, this line 0.4G, this line 0.5G, this line. So what does that mean? That on this axis, I can measure log of SA. Because the constant SA line, okay, is plus 45 degree line. Same way, you can repeat by taking the relationship between SD and SB. So SD is SB over omega. So that is SB into T over 2 pi. So log of SD is log of SB plus log of T plus some constant. And constant SD, let us say C2, and I bring that here. So I will get a constant SD. What is that going to give me? Log SB is equal to minus log T plus some constant. You agree? So constant SD line in SB, in log SB versus log T graph, it will be again a straight line with minus 45 degrees angle. So using that, I can get an axis here on which I can measure SB. So, or rather log SB. So on the same graph, I can plot SA, SB and SB. How it is possible? It is possible because these three quantities are related with omega. Okay. So simply multiplying by omega, I am getting either multiplying by omega or dividing by omega. I can get one quantity from the other. So it is possible to plot all the three together. And when I do this and I plot my response spectrum here, okay, I can read SA, SB, SB together, and what I get is the response spectrum is something like this. This is called tripartite plot. And what it shows, that there is a range in which velocity is constant, there is a range in which acceleration is constant, and there is a range in which displacement is constant. And another observation they have obtained, that this acceleration which I am getting here, this is alpha A times Pg. This is alpha B times Pg. And this is alpha D times Pg. This observation was made by Newman. Okay. So Newman showed that this constant acceleration, okay, we have done in the last semester also, and just now I have plotted. There is a range of period which we call acceleration control range. Okay, where acceleration is constant, and that range is controlled by Pg of the ground motion. Then there is a range which we call velocity control range, where the spectral velocity, pseudo velocity is constant, and that is governed, that is some constant times Pg. Okay. And then there is another range which is controlled by displacement, and it is some constant times Pg. Okay. So our response spectrum which we are using is representing all the three. Whether you plot it on tripartite graph or you plot it on normal graph. Normal graph means SA versus T. So here also, all the three ranges are visible. This is acceleration control range. Okay, this is velocity control range. So this is simply 2.5 times EPG. So that alpha A value is 2.5. Okay. If you look in Chopra's book, he has reproduced the table from Newman's paper, and there the coefficient for this are also given. So here is some constant, let me call it C V over T, and in displacement control range it is CD over T. Okay, different codes provide you the values in different zones of this value, EPGA, PGB, or the CV and CV. Our code, the shape remains same. Only one quantity is given, that is zone factor, EPGA. So the whole shape is multiplied by EPGA. We also discussed American code. In American code, what they are doing? They are giving two values. One here at 0.2 second and another here at 1 second. And then they give this value of TL, this period they are calling TL. So these three values they are given. Using these three values, you can develop the whole. Okay. Very recently in ESC 722, which has come only last few months ago. So they have given another type of response spectrum where they are giving the value of SA itself at 10 points. And when you join them, you get a smooth response spectrum like that. Currently they are using both the alternatives, either this or this. But soon they will migrate to this. We will talk about this, how this is okay. Our code is one step behind this, where we are giving only one value. Our code is also being revised, and in the revised code, these three zones will be given. But still, the shape is not changing from place to place, zone to zone. The shape remains same. Only value is multiplied. In American code, the shape changes because the relative value of this they call SS and this they call S1. So contours for SS and S1 are given, and depending on the relative values of SS and S1, the shape of the response spectrum may be too steep, it may be too flattened. Our code has just three shapes depending on the local soil. Okay. Then they have created a database for the whole country. You give the coordinates of that on USGS website. It will give you 10 spectral values at 10 degrees. And using those, you can plot the full curve like this. So, what is the next question which comes to us? From here, do you have any question? Or now you can do. You can obtain response spectrum at any site. Can you obtain? Yes? No? What question comes to your mind? If I ask you that now go to your site, obtain the hazard so that you can design your grid. Hazard, you are representing my response spectrum. That means response spectrum you have to obtain. So what will you do? What question comes to your mind? If you are using Indian code, spectral shape is given. What you need?
EPG.
EPG. So the next thing we need to do is how to obtain EPG. Okay. In our code EPG, if we are using American code, then SS and S1 they have given for their country. I want to use the same principle, same methodology here. What I have to do? I have to obtain SS and S1. How I can obtain these values? That is the next question. For that, we have to do seismic hazard assessment. And for seismic hazard assessment, we are using attenuation relationships. Or what we call predictive. What are these attenuation relationships? These are nothing but regression relationships. You know regression? Regression is fitting a curve to a set of data. Okay. So the data of the past earthquakes is with us. So we know the magnitude, the distance, and the corresponding value of EPG. Suppose I have this. So I can develop a relationship. That relationship is called attenuation relationship. And then the same relationship I can use at my site. When I am using it at my site, this is called predictive relationship. So same attenuation relationship is predictive relationship. Number of such relationships have been developed. All the seismologists who are working on hazard assessment, they try to develop their own relationship. So they collect the data for the past earthquakes and try to fit in such a relationship. Okay. In general, these relationships can be given as the hazard parameter y as a function of m, r and p. What is p? M and r you understand? P is path characteristic. M is magnitude of earthquake. And R is distance from site. Last class we were talking about if a large magnitude earthquake occurs far away, the effect or the intensity at my site is going to be low. And I am interested in the effect at my site, the intensity at my site, not what is happening at the epicenter. Okay. So I am interested in magnitude because larger magnitude earthquake occurring at the same distance will give me larger intensity. Then same earthquake occurring closer is going to give me larger intensity and path characteristics. What is included in path characteristics? In path characteristics, whole path, how the waves are traveling from the source, that is the epicenter, to site. Okay. This distance can be several kilometers to hundreds of kilometers. Okay. So whatever is coming in between, okay, you know how the earthquake motions travel from the source, those travel in rock. Okay. And then these travel through the local soil. Okay. Why it doesn't travel in the soil? Who stops it in traveling in soil? Okay. So for example, let's say I have my structure here or here, and this is a fault which is occurring, and you know on the fault the rupture can start at any point. The point from where the rupture starts, that point we call hypocenter or focus, and the point immediately above, this is called epicenter. Okay. Now from here the down motion has to reach here. What we assume is it goes like this and then it goes like this. Okay. Suppose it has to reach here, then it will go like this. It will not go like this. Why? Whenever we move away from the focus of the earthquake, the level of shaking reduces. Why it reduces? One reason is that as we go away from there, the area or the volume in which this intensity is distributed, that goes on reducing. For example, if I put a 100 watt bulb there, then just below this, the light intensity will be more. As I will go away and away, okay, that intensity will go on decreasing naturally, because there it is being distributed in more and more area. Okay. Secondly, if I put fog, there is a smoke in the room, then what will happen? The intensity at the same distance is going to be less. So this gap attenuation happens because of the distribution of the energy in the larger area largest surface area of that sphere, okay, and because of the dissipation of energy. Why the dissipation of energy takes place? Whenever waves pass through any material, the material vibrates, the vibrations occur, and in that process some damping is always there. So that damping will cause dissipation of energy. Damping of soil is much more than the damping of rock. So when the ground motion or the waves starting from the source, those are traveling in the rock, those are dissipating less energy. If those are traveling through the soil, they are dissipating more energy. Do you have any idea what is the order of damping in case of rock and soil? Soil? All of you must have some idea. 20%, 15%, 20%. That's what we talk about. Okay, in that range. In rock, 1 less than, okay, 0.5%, 0.2%, 1%. That's the order of the damping. So you can see there is huge difference of damping, and due to that, the energy in of the wave traveling in the soil will reduce very quickly. Okay, so it cannot travel much distance in the soil. It will get dissipated. So it travels through rock. In rock, it can go much longer distances, and then the effect travels through the soil. Okay. If it was traveling through soil alone, if earth was made of only soil, no rock, earth's crust was made of soil, then very soon the earthquake energy would have got dissipated. It would not have traveled so far. It is able to travel so far because the material through which the rock material, the crust material through which it is traveling, it is solid, okay, strong, okay. It doesn't go into inelastic range during earthquake. Soil goes into inelastic range during earthquake, and due to that, it dissipates a lot of energy, and that's why the damping is so large. Okay, so that's why it travels through the rock. So whenever we will be doing, we will first assuming that it will be traveling through the rock, it will be reaching below my structure, and then it will be traveling upward. Because when it is traveling through inclined path, the length of the path will increase, and the energy traveling through that path will reduce. Okay. So this is the epicenter. This is fault, and if I look it on the surface, the fault may look something like this. Okay, and here are my structures. So if I have to consider distance of the fault from my structure, which distance I should consider? This distance, or the shortest distance, or let us say here the epicenter was the point. This epicenter which I have plotted, this distance. And then not only here, should I consider this distance? Let me use another color. This distance. Which distance I should consider? How to define R? All these are possible. Okay. You have to keep in mind that whatever definition you have used while developing your regression relationship, in attenuation relationship, same definition you have to use while using that regression relationship as a predictive relationship. So when you are using it to determine the seismic hazard at the site, same definition you have to use. Okay. So all these, there are different attenuation relationships developed in which different definitions of distances have been used. So when you are using any attenuation relationship, you should be clear what definition has been used. Then similarly for magnitude also, there are different definitions. How many definitions of magnitude you know? The most common is Richter magnitude. Okay, the magnitude on Richter scale which comes immediately after the earthquake. Okay, that is also called local magnitude. Any other definition of magnitude you know? Just now you were saying something? Moment. Okay, so like that there is surface wave magnitude, MS. So ML, MS and MW. These are ML is Richter or local, MS is surface wave. This is used for long distance earthquakes. And MW, the moment magnitude. Okay. This is a representative of the energy released. W here. Okay, W is representing the energy, total energy released. Okay. And why it is called moment magnitude? So the energy released is the shear strength into area, okay, into D. Shear strength into area, what is that? That is the force multiplied by the displacement, rupture displacement. So tau into A is the rupture force required to cause that rupture, multiplied by D will give the work done. Okay, but it is also having the units of moment. W force into lever arm, that is also having the same thing. So that's why this is called, it is like the moment. I don't know, you can search in literature why they started calling it moment, but actually it is a measure of energy release. Then why don't we use this always? Why in the TV they tell Richter magnitude, not the moment? Why?
Because we need distance in the
Sorry?
distance. That is not.
D is displacement, not distance. So on the
Okay, displacement of.
fault, there is a shear stress developing. Shear stress into area gives you the shear force, and then how much displacement has occurred, that will give you the work done. Okay. So why they always talk about local magnitude, Richter scale per magnitude? Because that is the easiest to obtain. Okay. How Richter magnitude is obtained? Any idea? Empirical formula between what? Amplitude of ground motion and distance. Okay. So what you are actually recording? Are we going to the fault and measuring there how much displacement has occurred? No. We are only recording either an accelerogram or a seismogram. So from accelerogram you can get only the amplitude and distance. How do we get distance? From accelerogram? Any idea? You might have seen that seismological observatory. They tell how to get from the travel time difference between P wave and S wave. So looking at the accelerogram itself, they can determine when the P wave arrived, when the S wave arrived, and the difference in the velocity of the two and the time gap there will give you distance. So distance you will know from there, you will know the amplitude from there, and using that you can, so as soon as you get the record, first record, you can declare local magnitude. And how you will get this? For this you need to do lot of measurement. Okay. For this you need a large number of records from different directions. Once all that data is available, then you can calculate. But this is more reliable. Okay. So that's why you will see all the recent, latest attribution relationships are using moment magnitude. Okay. Old relationships, those are using local magnitude. And in TV, immediately USGS declares as soon as earthquake comes, there is automatic system which calculates local magnitude and intensity. This will take some time till all the data is compiled, fault geology is studied, then only they can come to this M term. So this takes some time. Okay. But different definitions of magnitude and different definitions of distance are possible, are there. And when you are using an attribution relationship, you have to keep that in mind. Okay. I will show you some simple type of attribution relationship. Okay, one more thing. How to get magnitude, which will be governing my set. What magnitude earthquake is going to govern my set? So for that, I have to consider all the faults in vicinity of the site. What is meant by vicinity? Nearby. How much near? Within a radius of 300. It is assumed that if it is farther than 300 kilometers from my site, the impact at my site will be negligible. I can ignore it. I need not to worry about that. How you will get the faults which are in the vicinity of my site within 300 kilometers? How to obtain those? Do you know any method, any source? Geological Survey of India. So GSI has published a seismotectonic atlas. It is available in our library. It used to be, perhaps now also has been transferred in the ground floor. You can go and see. So it gives us the map of different faults. GSI, it keeps on exploring wherever they find evidence of a fault, they explore it. Okay, and IMD is recording earthquakes. Okay, those earthquakes epicenters are known. So from those also we know where there is a possibility of from where those earthquakes are originated, which fault those earthquakes can be associated to. So using this information which we are getting from seismotectonic atlas and IMD past earthquake records, this will give us an idea of different faults within 300 kilometers. Okay. So once I know these faults, what is given in seismotectonic atlas are plots, maps of those, and we see generally only the surface projection. Okay. So GSI is giving me surface projection. And when I look at the earthquakes records, those are giving me certain area. So if you look at seismotectonic atlas, some lines are plotted. Those lines are representing faults. Okay. If you look at the IMD data, you will get clusters, some areas in which earthquakes are occurring. Okay. So you can get an idea of the area of the source or the length of the source. Okay. How to get magnitude, corresponding magnitude? For that, again, you have to use some empirical relationship, the data from past. And one such relationship, a famous relationship, Welsh and Coppers. Okay. Folders. whatever I am teaching in these classes is available in Kramer's book. Okay, so you can look at Kramer's book. This is PDF or PPT? नहीं मैं तो PPT चाहिए हमारा
So last one.
Okay, so this is the relationship. I have taken it from Kramer's book. Originally it was published by Welch and Crawford Smith. And what you see here, the relationship between magnitude and length, and then magnitude and area, and magnitude and rupture displacement, dr. So, okay. And reverse relationships are also given. Relationship between magnitude if you want to calculate length of a magnitude. Okay. So just using this, it will be interesting. Calculate the length of the fault which can generate a magnitude 9 earthquake. Please do that. If a magnitude 9 earthquake is coming, what length of the fault it will require? Just put MW is equal to 9. And what you see here, there is strike slip, reverse, normal, or. Do you understand what is strike slip, reverse, and normal? Anybody? Like this, all the faults go like this.
Slightly, two parts of the soil go over each other. Like,
How will
One part, two parts of rock crust, because rupture occurs in earth's crust. Soil does not rupture, only rock can rupture. Okay, what will happen in soil? Soil will simply deform. If that pressure was building in soil, soil will simply deform. Okay, it will fail gradually. Okay, it will yield, but rock is brittle. It doesn't yield. It go on storing the strength or the energy, and suddenly it breaks. And that's the problem. That's why we get earthquake. If soil surface, rock crust was made of soil, there would not have been any earthquake. Okay. So the rock ruptures. So that rupture can happen in different ways. Generally, at a rupture, you will have this type of situation. Okay. Here, this side is called foot wall, and this side is called hanging wall. And recently, they have discovered that the same magnitude earthquake will have different ground motion characteristics on foot wall side, different ground motion characteristics on hanging wall side. So this also makes a difference, that whether your structure is here on this side or it is here. So hanging wall and foot wall also make a difference. Okay. Now which wall to call foot wall and which wall to call hanging wall? Try to stand on this wall. Then the wall on which your feet will be there. That is foot wall. So when you will stand on this is the foot. You can't stand like this. So this is the foot wall, this is the hanging wall. Okay. So if any movement is occurring in which the hanging wall is moving downward as compared to foot wall, this is normal. Reverse of this, when hanging wall is moving up as compared to the foot wall, this is reverse. And what is the strike slip? This type. And what is oblique? It has both. This is called dip. Actually, it is given by the angle normal to the plane. So this is dip. Okay. And this direction is called strike. So strike is like bearing. So if the fault is appearing like this, you take the angle from north. Okay, that is strike angle, or the bearing of the surface rupture, surface manifestation of the fault. Okay, so that is a strike, and as the name suggests, dip, how it is dipping into the soil inside. That is the dip. So movement can occur like this, or it can occur like this, but mostly it occurs like this, which has horizontal as well as vertical component. Okay. So it moves along the dip as well as along the strike. Okay. So that is oblique. In this study, they have classified into 3 categories, or rather 4 categories: strike, reverse, normal, and all. All means when they are not bothered. Then, because regression is what? You just have some output, some input, and between them you are fitting an equation. Okay. So this equation, when they are fitting, they are getting this. When they consider only strike slip faults, they got this relationship. When they considered all, mixed up all, then they got this relationship. Okay. So let us see when we consider this relationship for all, and I want to calculate length corresponding to magnitude 9. What length you are getting? It will give you an idea. And here the distance L is in kilometer. And area is kilometer square. Calculate.
For strike slip.
For all. So log L is 0.69 into 9 minus 3.8. Hmm? 977. Is it correct? It appears to be too much.
It is 19.88 kilometers.
No, that's also not correct. Huh? Log to the base 10. Of course, that is ln, natural log. Log to the base 10 you have to use. उसमें ही आएगा 8 का जरा कीजिए 8 magnitude 190. That's okay. So how long the fault has to be if 9 magnitude earthquake has to occur? How much length it has to rupture? About 1000 kilometers. Okay, 8 magnitude earthquake. Do you have any idea how much was the rupture length in case of Nepal earthquake, recent Nepal earthquake? What was the order at least? 20 kilometers or 1000 kilometers? Where? between 20 and 1000 volts. 90 kilometer. Any other guess? It was about 250 kilometers. Okay. So such huge length ruptures. Then it generates magnitude 8 and 9. And from 8 to 9, how much jump? Huh? Why? Why so? How many times the energy increases when we go from magnitude 8 to magnitude 9? Huh? 30 times, not 10 times. Okay, it is log scale, but it's not increasing by 30 times the energy increases. Okay, but you will see later the intensity, fortunately, does not increase 30 times. Energy increases 30 times, but the PGA, if PGA would have increased 30 times, so PGA fortunately does not increase 30 times. Why? What may be the reason? The rupture increases from 200 kilometers to 1000 kilometers. Energy released increases 30 times. Okay. PGA may increase, let us say, by a factor of 2 or 1.5 in that range. Why so? Why the PGA also does not increase so many times?
The area covered is very large.
Yes.
But
But that is in all the cases. When 8 magnitude earthquake is occurring, then also it is the same radius. When 9 magnitude earthquake is occurring, then also it is the same radius. So area is same. Area of the sphere is the same.
As compared to the length.
No, I am considering if 8 magnitude earthquakes occur, let us say 40 kilometers from my side, and 9 magnitude earthquakes comes at 40 kilometers from my side, then the PGA is going to increase something like from 0.4 or 0.6 to 1, something like that. That type of increase I am having. So why the amplitude is not increasing 30 times?
Because length is increasing.
Length is same. Length of, oh, you mean length of the fault. Okay.
Length is more than the energy dissipation is more. You can say that.
Energy dissipation will depend on the fault line. It will depend on the distance of my side from the fault, not on the fault. So one thing is that energy is proportional to square of amplitude. You remember from high school wave propagation? So energy is proportional to square of amplitude. Okay? One thing. Secondly, as the intensity of the shaking increases, the strain in the material through which that energy is getting transmitted increases. And damping depends on strain. Damping is not constant. Damping depends on strain. As the strain, larger and larger strain occurs, okay, if strain is too high, then yielding will occur. So the strain depends on the amplitude. Okay, and damping depends, that means energy dissipation depends on amplitude. Okay, so dissipation of energy will also be faster. In case of a larger magnitude earthquake, the earth crust will dissipate that energy faster. And amplitude is not proportional to the energy release, rather it is proportional to the square root of energy. That's why the PGA is not increasing by the same order. Okay. The increase in the PGA is of much lesser order. Okay. So I just wanted to give you an idea how. Okay. So our time is over. Okay. So we will stop here, and tomorrow when we will meet. Tomorrow we are meeting at 12. When we will meet at 12, I will tell you in this background how I can predict the EPGA at a site. I know the fault, now you can guess. I know the fault. From the fault, area, length or displacement, I can get magnitude. Once I know the magnitude, I have to see the distance of my site from the fault, and then using an attenuation relationship, a regression relationship from past earthquake, I will apply at my site, and then I will get the PGA or PGA at my site. So I need to know some of the attenuation relationship.